Juliana. Okay, so welcome everybody to the seminar of the International Institute of Physics. And it's a pleasure to introduce today Dmitri Khveshchenko from the University of North Carolina, Chapel Hill. He received his PhD from Landau Institute in Moscow, and after that he spent some years as a postdoc at University of Chicago and at Princeton, and he spent also some years as an assistant professor at the Nordite Institute when it was in Copenhagen. And somewhat 1999-ish, in 2000, he moved to North Carolina. So he works in condensed matter and electron structure of strongly correlated materials, and also in more general questions about relations of quantum field theory with properties of quantum matter. And he's also known for his critical approach to ADS-CFT correspondence and applications to condensed matter systems. So today, I think we'll hear a little bit of everything. And please, Dmitri, the word is yours.
Thank you, Dima, for this introduction. And of course, thanks a lot for the opportunity to visit here again. So it's a pleasure. I would have talked about holography because I have quite a few things to share. And I've been rather vocal on that issue. Speaking of a very specific take on holography, namely its alleged applications to condensed matter physics. But instead, so they'll talk about something which is by no means novel. All right. Specifically, I will touch upon a number of issues involving the sort of substance such as graphene or similar semi-metals in 2 dimensions, which you can think of as monolayers of that material. And in particular, I'll be concerned with such issues as whether or not graphene, for one, can be thought of as an ordinary Fermi liquid and remain such down to the lowest temperatures, or perhaps not. In particular, we'll address the effects of disorder, which are rather peculiar in this context, the effects of magnetic field and interactions of the sort of realistic nature, as opposed to something which is easier to model, but may not be that physically relevant, short-range interactions in particular. Well, if time permits, I will speak of the possibility of even using graphene as a sort of desktop environment for simulating some of the alleged holographic type of phenomena, which also proves that there is no big physics behind it, but there might be some appearance of holography. Okay. First, I'll briefly mention some of the single particle effects involving Dirac type fermions, of which there are quite a few. I'll then move to the central topic of this presentation, that is the effects of Coulomb interaction, either without magnetic field or in its presence. And I will discuss what might be called in the field theoretical context chiral symmetry break in magnetic catalysis, for which the more mundane condensed matter type of names would be exotonic insulator and quantum Hall ferromagnetism, respectively. Well, like I said, if time permits, we'll get into the topic of simulated holography too. As you can see, all of that stuff was published quite a while ago, and I thought it would be, known in the community until like a couple of months ago, when I started noticing papers. 18 May, magnetic catalysis and weakly interacting hyperbolic direct materials, including graphene. 10 days later, a review of interaction effects in graphene. Earlier this month, there was a paper, which I will refer to a number of times as the talk progresses, interesting, none of which cites any of the publications that I presented earlier. So it might be a good opportunity to remind people interested in the topic that some of this, if not most of this, had been studied before. Carbon comes in many different forms, allotropic forms. Curiously enough, diamond, which you might think of as the hardest and most stable material, at ambient conditions is not that stable and loses to multi-layered so-called pyrolytic graphite. That's the actual ground state of carbon in the many multi-atomic assemblies. What we need to know about graphene as a single monolayer of carbon atoms is that the spectrum of electronic excitations near the so-called Dirac points, which sits right in the middle of the spectrum, is mathematically similar to what you might think of, say, neutrinos. It's linear within an energy range of order of an electron volt, which is comparable to the bandwidth of graphene. But of course, the velocity, the corresponding Fermi velocity at those isolated Fermi points is about only 1% of the speed of light. So those electrons, electronic excitations, are of course non-relativistic, but they have the appearance of some ultra-relativistic particles propagating at their own speed of light, which is about 100 times lower than the actual one. Okay? What this requires one to do then is to consider electronic states both above and below the Dirac points, including them into the full description of the corresponding wave function, thereby provide that wave function with the sort of, so to speak, particle and anti-particle components. Okay? Or again, in a conventional condensed matter language with an electronic as opposed to whole contributions. Technically, it will look like this. If on the left you see the hexagonal lattice in the coordinate direct space, and on the right that would be its dual reciprocal unit cell in momentum space, then what I've just said implies that the wave function of those excitations would have to be composed of four components for either direction of spin. Spins here would be represented by sigma, and before the magnetic field is turned on, everything is going to be insensitive to the spin orientation. So that would be a dummy index up to a certain point. As to the four components in question, those would represent the sort of low energy excitations made primarily out of the waves with the momenta close to either one, let me call it L, or the other, let me call it R, distinct Dirac points. You may think there are as many as 6, but in fact, this L combines with those two at 120-degree angle, and that R combines with the corresponding pair. So it takes 3 such points at the edge of the Boolean zone to comprise one Dirac point. And then each of these species may live on either one, called A, or the other, called B, sublattice, triangular sublattice of the hexagonal lattice in the coordinate space, which is why it takes 4, right, for each value of the spin variable. And then the Hamiltonian for these non-interacting neutrino-like excitations would look like this, where you have to use some sort of gamma matrix contracted with the gradients in the real space. So one thing that can happen, the sort of simplest but non-trivial thing that can happen to these excitations is that they would all of a sudden develop a mass in their spectrum, which again, in the condensed matter context, we would call a gap, thereby turning what used to be a semi-metal into a semiconductor with a truly gapped spectrum. Okay? If the chemical potential sits right in between, the lower valence band is full and the upper conduction one is empty, well, we're looking at a semiconductor then. Now, this type of phenomenon has long been under the discussion in the sort of fundamental field theory, among other things, where something similar would be frequently discussed as a scenario known as chiral symmetry breaking in, for example, 3-dimensional QED. Now, the theory of graphene, and I will make it clear on the next few slides, is not quite the same as QED, but shares certain common properties, which is why the story starts with this model, which, unlike the theory of graphene, is indeed Lorentz invariant. Right? It has some fermions whose number n is a parameter. The other parameter being the coupling constant G, which controls the strength of this Maxwell term. Turns out that for the phenomenon in question, the value of G is unimportant. And that's a peculiar feature to keep in mind. But the number of the species is. Okay, number of those flavors is important. So here's how it works. On the classical level, one can easily check that in the absence of any mass, the theory allows independent so-called chiral left and right rotations. And that's the full symmetry U of 2n of such a model. Once the theory develops a mass as a result of this spontaneous, obviously, phase transition, the original chiral symmetry gets broken down to the product of two UNs, left and right, independently. And interestingly, the phase diagram of this model demonstrates that at, say, 0 temperature, it will happen for n lower than a certain critical value, but is not expected to occur for n that are greater. Right? And then as temperature goes up, the domain where the symmetry breaking is going to happen shrinks, and eventually you end up with a phase diagram like this. So as I said before, there must be a critical value of the number of fermions in this model. And it does not impose any conditions on the coupling constant itself. That's basically because this Maxwell coupling appears to be subdominant to the induced, if you like, kinetic energy for that variable A, the gauge field, which is the result of the polarization of the fermions themselves. Okay. Before I proceed with this scenario any further, let me just mention that there have been similar scenario discussed in seemingly unrelated context. For one, one could contemplate the idea of developing a secondary superconducting pairing on top of the already present one, specifically in the context of the high TC cuprates, where it's more or less well established that the gap is of the so-called dxy squared, x squared minus y squared nature. But there have been some rather numerous, actually, circumstantial pieces of evidence that perhaps there is a second gap developing at a certain point of either IS, what's called, or ID, and you should think of the lattice symmetry, so it's dxy, which would then play the role of a mass of the otherwise massless quasi-particle excitations near the nodes of the primary order parameter, which are at these two and those 2 points. Okay, that's a separate story, but mathematically very close to the one in graphene. Well, the other parameter is a trace over that flavor index. So it's psi1, bad dagger, psi1 plus all the way to n. That's why it retains some symmetry with respect to the left and right rotations. And the number of, well, what basically controls is number of gallstones that one can expect in this system once the chiral order sets in. Well, that's the one which is most likely. No, if you're talking about, if you're asking me about this high TC thing, well, again. Right, but if they're flavored, it would be thought of as a trace over that non-dynamical. number of species. Well, in BCS, we don't have that flavor index. What we do have is the spin, and it has to be, if it's all about the D wave pairing and S wave as opposed to P, it has to have 0 spin as a pair. Right? So it's a singlet combination. But like I said, I'm not discussing the spin-related effects yet. Instead, I have this artificial number of flavors n. Spin may play the role of that flavor when it's not dynamically engaged, when there is no magnetic field, for one thing. So just to mention a few of the curious phenomena which are rather sort of counterintuitive when it comes to the dynamics of pseudo-relativistic particles. Of course, number one is the so-called Klein paradox, which is not a paradox, it's a fact of life, according to which, if you have this neutrino-like Dirac particle with no mass, 0 mass, and it flies towards a barrier, instead of bouncing off, if the height of the barrier is larger than the energy of the combined particle, it goes right through. The transmission coefficient is actually 1. The only way to decrease it below 1 is to have at the incidence level or different from 90 degrees. But at normal incidence, it's exactly 1. One can think of the sort of natural transformation of what appears to be a particle outside the barrier, which naturally converges or converts itself into a hole, or what looks like a hole under the barrier. And then if the barrier has finite width, it will recover on the way out. Apart from being peculiar, this also means it's difficult to actually make any good use of graphene, in particular when it comes to building transistors, because you would like to have the means of stopping a current from flowing by operating this device electrostatically, and it's just not going to happen, right? Electrostatic operation doesn't provide you with the knob to turn it on or off. And so the best that people were able to achieve was the so-called ambipolar transistor, which is sort of open, sort of closed, but not completely. And in that regard, it would be nice to have a mechanism or means to turn the gap or mass in the spectrum on and off when necessary. And that will be one of the main themes that I'm going to follow in this story. Okay. Then another peculiar phenomenon is a so-called atomic collapse, or the existence of so-called critical charge, whereby an atom may collapse without any radioactivity, even with a perfectly stable nucleus, if the charge of the nucleus is so large that it's actually greater than 1 over alpha, alpha being the fine structure constant, which means it's going to be greater than 137. And there are no such atoms that we know of. But if there were, it would then result in the electrons' orbits becoming unstable and spiraling down to the core, to the nucleus, where they would collide with the nucleus, decrease its charge by 1, and will continue with the outside orbits until the new charge drops below 1 over alpha, and then it stabilizes itself. Okay? So it's atomic collapse without radioactivity. A sort of little known but curious phenomenon. Huh? Because physically, because if you solve that hydrogen atom problem in a relativistic setting, right, at some point, when this happens, the ground state drops below the minus mc squared in the particle Hall continuum, and so it creates a pair out of vacuum. Okay. Literally, that's the gist of it, right? Well, there have been also interesting proposals regarding the ways of making a so-called ideal lens, not for light beams, but for the electronic waves, though, that would be focused below the diffraction limit, proposed quite a while ago by Vesilago. Which may be interesting and important in terms of well, lithography, how you create microchips with the electronic etching. But I'm not an expert to speak about. Now, speaking of many-body phenomena, there have been lots of speculations about possible superconductivity in graphite at that time, how it was called, or graphene soon thereafter. Nowadays, they would be talking more about the regime of strong doping, when the chemical potential sits not at the Dirac point, but fairly far away from it. Better yet, in the vicinity of one of the so-called Van Hoff singularities, where the electron-phonon interaction gets strongly amplified. Also in the context of the so-called bi or tri-layers near the, if they are rotated with respect to one another, and the angle hits one of those magic angles which are low, of order of 1 degree or so, but there is some interesting behavior at those rotation angles. There's a whole still not quite explored, not completely explored, but being actively explored, a zoo of the various correlated states near those orientations. Or perhaps in the case of tri-layers, one doesn't even need to rotate. Superconductivity will set in by itself. This is again, something people are into nowadays, and not all the answers are known. Which is why I would choose to talk about a different kind of pairing, which is also related to that issue of whether or not a gap can be operated manually, if you wish. And that is the story of the Exitonic gap, which instead of occurring in the particle-particle channel, that's what we call superconductivity, ought to emerge in the particle-hole one. Right? So it's the neutral compound particles that we call excitons that may or may not occur. Well, now historically, that was stimulated by some rather mysterious experiments that I understand were carried out in São Paulo. One of the names, Kotelevich, Esquinazi would be his German colleague. And so they advocated for quite a while this point of view that perhaps even the most mundane so-called highly oriented paralytic graphite harbors a number of subtle many-body related phenomena, which the community didn't seem to be readily embracing at the time, at least. But I thought it was an interesting possibility to explore. And perhaps the paper I referred to earlier, which was released earlier this month, may or may not have something to do with it. But should this be possible to achieve, it would open up the possibility of various, even applied uses for graphene. Of course, gap band engineering is what I refer to as the possibility of turning the mass on and off. Electron confinement, which comes with it because the ordinary excitations do not have that property of Klein tunneling. They would bounce off a barrier if the barrier's height were within the gap. Tunable frequency lasers would be potentially attainable. And also one could try to think of making graphite ferromagnetic by design, right? Which, again, for microelectronics would be quite useful. Now, speaking of the theory of this phenomenon, here's what one actually deals with. This is the Hamiltonian of graphene, where you see that kinetic energy, which has this relativistic-like appearance, right, with the velocity, Fermi velocity, as I said, being only 1/100th of the actual speed of light. But the potential term, the interaction is still taken in the simplest form of the Coulomb coupling with no retardation whatsoever, because the actual photons are fast compared to these electrons. The actual photons propagate almost instantaneously, and so the interaction term has no retardation in it. What one would like to do is to, say, calculate the electron propagator, which would reveal a host of properties that are amenable to being tested in photoemission, tunneling measurements, transport to, and so forth. So that's what we might be after. And of course, here I would first allow for the possibility of having some magnetic field, which now splits the energy levels, and that's the ordinary Zeeman splitting. But I would also allow for the mass gap, even if it's sort of only virtual, and may or may not actually develop. Okay? As to the effective interaction, well, as I alluded before, it's governed not only by the bare interaction of the Coulomb nature, which is what goes as one of the transfer momentum, as opposed to the square in 3 dimensions, right? But also receives an important contribution from the polarization of those fermions themselves. And the peculiar feature here is that, at least in the static limit, it's of the same nature. It's also linear in the transferred momentum Q, okay? And so it's not something which dominates over the bare term, as it happens, by the way, in QED3, which I started out with. Right? Here it's on par with the bare interaction, and everything combines. Now, the parameter of interest here is this analog of the fine structure constant, which I could have mentioned earlier in the context of that atomic collapse problem, which, unlike the fine structure constant in our physical 3-dimensional universe, is not small. It's not 1/137. It's actually greater than 1, but depends on the dielectric constant of the surrounding medium. Okay? So if this graphene monolayer sits in vacuum, they call it freestanding, then epsilon is 1. If it's sandwiched between, say, silicon oxide, which would be rather commonplace, especially in the early experiments, then it drops by a factor of 2. Okay? If it's deposited on the substrate of hexaboride, it drops even further. But so it depends. But in either case, that effective coupling is large, not small. And so we want to reiterate that the interaction is different from being essentially a contact one with the Fourier transform that is independent of the momentum, nor is it weak. It is a strong interaction. So at this point, one can proceed in a more or less standard manner, exploring the solutions to the so-called Schwinger-Dyson equation for the self-energy, trying to solve it self-consistently. And a number of things can be pointed out here. First, as far as the diagonal part of that normalization described by this equation is concerned, well, there is some effective momentum dependence of the velocity. The thermal velocity acquires some momentum dependence, which translates, by the way, to some anomalous power law, or at least that's what it looks like when promoted from first 2 orders to the high orders. That's a potentially important but not crucial type of renormalization. The crucial one is encoded in the off-diagonal part of this equation, which is actually for the, so to speak, matrices, because that gap lives in that 4-dimensional space of the Dirac spinors. So strictly speaking, one has to think of the matrices, and then they have diagonal versus off-diagonal parts. But what this off-diagonal part contains is the equation for the gap itself. Curiously, one can transform this integral equation into a differential one, complete with some boundary conditions. That's a rather well-known trick, which I thought, was something original, but turned out that people had known about one time. The solution that comes out of this equation is quite different from what we know as the standard mean field BCS, because the BCS as a function of the relative momentum of the pair would be just a plain constant. Instead, it's a rather non-trivial function that varies as a function of the relative momentum of the particle-Hall pair. So it has this strongly non-BCS type of nature. And yet, you can work with this function for pretty much every need. The story gets even more interesting if the kinetic potential is shifted away from the Dirac point, so that there are some excess of particles and holes in the system. But in the symmetric case, what's important is that the non-trivial solution, the gapped solution, requires the coupling constant to be in excess of a certain critical value, okay? Which can be evaluated as exactly 1/2 if one neglects the before mentioned velocity normalization. If it's there, if one wants to account but different, so it's that critical value of 1/2 picks up some corrections. But more importantly, the gap itself has this sort of conspicuously looking form, which those familiar with the theory of Correspondence transition may recognize it as dependence on the coupling constant as opposed to temperature, which it would have been if it were a Correspondence type of transition. Both actually are of the same conformal transition type, as they're called, or Miransky transitions, sometimes they're called. So that would be the behavior of the gap as a function of the coupling G in excess of the critical one, which is 1/2, in the absence of velocity normalization. If one accounts for it, well, then it changes to a power law dependence, but still requires a threshold, the coupling to be above a certain threshold. Or one can try to solve it by constructing this phase diagram in the inverse coupling versus the number of species plane, and so forth. Now, physically, this development of a non-vanishing mass or gap is very simple to picture. It's nothing but a formation of what we call charge density wave, where half of the sides of the hexagonal lattice find themselves with increased, above the average value, increased electronic density, and the other half has a depleted. So the charge density wave forms, and it translates to having that gap in the spectrum. Now, how does it compare to the actual values? Well, the gap equation, which was solved originally, turned some critical value just above 1, or if you artificially send it to infinity and consider this kind of graphene on steroids, well, then the critical number of species is slightly greater than 7. Okay? Now, in real life, as I already showed before, for freestanding graphene, the coupling would be almost twice that. Okay, whereas it would be suppressed below 1 if it were sitting on a silicon oxide substrate. And of course, the actual value of n in the absence of the magnetic field induced polarization is 2, spin up, spin down. Now, interestingly, the Monte Carlo simulations, the best ones available at the time, revealed the critical value very close to the one obtained from the naive solution of the gap equation. I think it's a pure coincidence, but a pleasant one. Okay? And then there was also some fairly large value of the number of species in the artificial limit of infinitely strong interactions. I should say that Joaquin Drat actually came to our department a couple of years later He's now my colleague, but after he moved to UNC, he stopped doing graphene altogether. Didn't help, although I had been hopeful. That's why I myself drifted away from that stuff. And by the way, speaking of the mechanism of formation of this gap, what I've said so far pertains to a single monolayer. And of course, if we have a stack in the so-called highly oriented paralytic graphite, the stacking is in the what's called AB, or out of registry configuration. So the atom is sitting in one layer, has an empty, as a void above in the adjacent layer, and so forth, and vice versa. And that configuration actually further increases the tendency towards developing a charge density wave within the same layer. Okay? So the solid residue of all that discussion would be seemingly that we should expect to find that gap in nature. Right? And then, if so, we would be looking at the sort of generic phase diagram of graphene, or graphite, as it was called at the time when all these predictions were made. Graphene wouldn't have been synthesized until 4 years later. Would look like this. So if we were looking at graphene in vacuum, we would find ourselves here at the coupling constant greater than the critical value. Okay, so that is at low temperatures within the ordered phase with a non-value. And as you keep on raising the temperature, where the temperature is too high to observe the gap directly, but the behavior within this whole range would still be different from that in the absence of any gap. It's a more subtle effect of how one can detect the presence of a gap above the transition, but it's a known scenario, and there are means of doing so, which I will address a little later. On the contrary, if we were to put that graphene on a silicon oxide substrate, we would find ourselves here in the subcritical region, where there is no gap emerging, but at sufficiently high temperatures, there would still be this window of opportunity, literally, to say something about the nearby quantum critical transition at zero temperature. That's a rather famous Sajicev scenario of what one can tell about the phase transitions at zero temperature by looking at what happens to the system at high temperatures within the quantum critical phase. Okay? And there are specific prescriptions of what to look for. So we don't know if all those estimates were actually meaningful, because the later studies, which I sort of read about but didn't quite follow, seem to indicate that perhaps those earlier results underestimated the effects of the local screening of the Coulomb interaction by those multiple inner orbitals, which would have made the Coulomb interaction weaker. Okay, and then would probably put us far to the right and away from that interesting regime, and that would be like the gap never develops. But at least in the beginning, the story looked very promising. Once you make a prediction, people tend to observe things. So one of those first evidences, or it looked like one, came out of the ARPES, angular resolved photoemission studies of graphene, which reported a rather large gap. Something which indeed looked like one. Shortly thereafter, it was claimed to be observed in tunneling studies, albeit by order of magnitude lower. It still looked like a gap, a legitimate one. And even some rather tedious analysis of the host of transport data seem to be suggesting a certain value of the gap, which would fall sort of in between the ARPES and tunneling values. Needless to say that after a while, all these results were withdrawn. They had been published, though, in the meantime, before the authors retracted them. PRL, Science, Nature. Speaking of, how critical one should be in general of some sensational reporting. So now we think, now the consensus is that, well, unfortunately or fortunately, pristine graphene, freestanding even, the one that I would place safely on the left of the critical point, is not gapped. Okay, there seems to be no solid, as opposed to, well, the immediate evidence supporting this scenario which I just described. Okay, one way of explaining this would be in reference to the stronger effect of the screening by the internal orbitals as compared to what one can evaluate naively and use as the values of that effective coupling constant G. But the story doesn't end here. Yeah.
So these experiments were done for substrates, so that this is the case where...
At that time, those were the only ones they could do, yes. Well, again, you don't quite know where to place yourself. Yes, yeah. Well, the point is that we don't quite know what that parameter is. We could have underestimated it, but most likely, judging by the sort of current consensus, we overestimated it to begin with. Okay. Well, still, it's not the end of the story. And we were prepared. Well, for instance, one can still make some non-trivial predictions about, say, the shape of the ARPES curves, which one would call the damping of those excitations, even if there were no gap, but the peculiar Dirac-like kinematics would still have its imprint. The behavior of that damping is kind of different from the naive one. Same goes, I won't delve into the details here, just mention things. Same goes for the channeling data. One could make specific predictions what to look for even in the gapless regime that would be indicative of the Dirac type of excitations, as opposed to the conventional Fermi liquid-like quasi-particles with a Fermi surface. I'm not sure if it's been pursued further than some early data, but those claimed the agreement with these predictions, even in the pessimistic scenario of no gap. Further, one could entertain the possibility of discussing this mechanism at finite doping, and that brought out the such thing as lifting of the spin rotation symmetry, so that the exotonic condensates would occur differently for the singlet versus triplet spin configurations of the particle-Hall pair. That in itself, although this is another story, this in itself would have explained that mysterious magnetization, first reported in the data by Kopilevich, Esquinazi, and others. Right, so that would be a possibility to explain the otherwise, too low a value in terms of Bohr magneton per carbon atom, yet, according to the authors, a robust ferromagnetic-like order present in their samples. Although, in all the fairness, I should say that one could invoke a number of simpler, single particle, essentially, mechanisms, those including magnetic impurities, which the authors claimed they had gone a long way to get rid of those, structural defects, physical edges, dangling hydrogen bonds could all be the sources of some local most likely boundary bound magnetism, as opposed to something that happens in the bulk and has this interaction-related nature. But that would still be on the list of possibilities. Now, let me switch gears and talk about something which, again, I will start out as a non-interacting picture and then will include the Coulomb interactions into. And that's the story of quantum Hall effect, which, of course, was first observed and studied for decades in such traditional materials as silicon or gallium arsenide. And it came as a big surprise first that in graphene, the same quantized behavior of the Hall conductivity was observed not at the helium, but at room temperatures. Of course, this has everything to do with the robustness of the Dirac linear spectrum on a scale of 1 electron volt, which is 10,000 Kelvin. But it also had its peculiarities. It was different in the appearance of the plateaus. There's the middle step, which is twice as big as that of the sort of conventional, or let me call them non-relativistic, mathematically speaking, systems. That was different. And furthermore, it would also raise the hopes to observe a counterpart of this gap opening mechanism now induced by the magnetic field. So it would not only be related to the Coulomb attraction, but it would actually require an application of magnetic field to occur. Well, to decipher a little bit this picture, one can start out with the spectrum of the relativistic Landau levels. Even in the absence of the gap, they would, roughly speaking, scale as a square root of both the field and the levels number. And of course, this is very different from what you're used to in the context of non-relativistic quantum Hall effect, where the dependence on both would be linear. Okay, but that's because it would be then linear as a first order term and expanding over the field as compared to the large mass, which is the actual free electron mass of half of MeV. Okay. So the sequence, as I just said, the sequence of the plateaus would then be slightly different, but noticeably different. And that's what people who studied quantum Hall effect in graphene first reported. And it would be quantized in units of 4. Those that number stemming from the product of two factors of 2. Of which one factor would be the number of spin components, and the other the number of those Dirac points, or as they are often referred to, valleys, left versus right, as in the beginning of this presentation. Altogether 4. Okay, so the sequence of those plateaus and their evolution with the field were suggestive of the following. At fairly weak fields, below, say, roughly 10 Tesla, there would be no particular evidence for the formation of any mass here. Okay, but and that's what the quantum Hall effect measurements of the first generation reported. But at stronger fields, as it turned out. There was some evidence obtained of the splittings, which would be consistent with saying that, well, the gap might indeed develop. And in particular, they observed the new fractions, new plateaus, which would, again, suggest that something of that kind might have been happening. And even more importantly, they did not observe some other plateaus, which would be possible to reconcile with the simultaneous spin and valley splitting. Okay? And even further analysis showed that the new plateaus developing at, well, specifically the fielding factors 1 and 4 would scale differently with the field. This is all about the strong fields. Above 10 Tesla and up to 30, I believe. they seem to have seen the linear splitting, which would suggest the Zeeman and therefore sort of trivial nature of the corresponding gap, as opposed to a square root one, which one could indeed expect in the case if it were the result of the Coulomb interactions. Okay. And when it comes to the latter, well, one could repeat the calculation which I presented before, now in the presence of quantizing magnetic field. And it turns out that in contrast to what happens without the field, here, it does not take any threshold. The interaction does not need to be stronger than a certain minimal value in order to develop a gap. Right? It's there. The confining factor is rather the filling fraction of the Landau level in question. So that gap would vanish when the Landau level is either empty or completely full, and that is to be expected. That takes the maximal value when it's half filled. So that would be a sort of a theoretical mechanism for developing the magnetic field dependent gap, and sufficiently large fields, it would scale as a square root of the field. And if one were to use this graphene with the field applied for making transistors, well, that would be perhaps some additional knob to turn. Okay. Well, the people who were also interested in that stuff at the time went to great lengths of actually processing and comparing the data, and claimed that, say, at 30 Tesla, the gap would be indeed 50 Kelvin or so, similar to what the theory predicted. And again, what was reported earlier this month may or may not have been related. Okay, I don't know. My attempts to contact the authors was not successful. Nor did they mention any of that earlier work, for that matter. All right. Again, for the fairness, I should mention a number of alternate predictions and possible explanations. Some people prefer to call pretty much the same scenario. They call it quantum Hall ferromagnetism, but its nature is the same: Coulomb interaction in the presence of a magnetic field. Some would refer to such single particle mechanism as spirals distortion. I'm not going to talk about this, which doesn't require any of that. So we still don't know, but it might be more interesting than it seems. Okay. And of course, those mysterious Kopilevich's data can be processed this way to show that the gap extracted from those data would sort of resemble the square root dependence in question. But again, whether this is another coincidence, fortunate and unfortunate, I would not know. Also, I should mention that on the basis of this picture, one could predict some new fractions in the fractional quantum Hall regime. And again, I'm not going to talk about this, especially in the context of what's called composite fermions, composite Dirac fermions now, which was developed for that purpose. My understanding is that similar new fractions were found in the numerical studies, but I haven't seen any evidence in actual experiment. All right. Now, I'm almost out of time, but I still want to touch upon another topic, maybe not holography. I'll be happy to talk about this next week or privately. But let me mention the effects of disorder, which are kind of like the single particle phenomenon, but comes with a twist. When you have these Dirac fermions in graphene propagating in the presence of some disorder, well, then there is something that distinguishes them drastically from their counterpart in the ordinary Fermi liquid, silicon or gallium arsenide. Because in the latter, what people usually talk about in two-dimensional case is the interference between the trajectories that those wandering particles take and their time reversals, which go the other way. And it's the constructive interference between these two that enhances the probability of backscattering. So every time that electron hits an impurity, this impurity scattering event gets amplified. And that, of course, stops the electron from propagating in the first place. It means localization, or weak localization in the two-dimensional environment. What happens with the Dirac fermions is right opposite. The built into chirality of those excitations, which also manifests itself in the Klein tunneling phenomenon that I talked about, gives rise to the extra phase of pi, so that the two trajectories, which are time reversals of each other, instead of adding up, subtract. And therefore, this quasi-particle would experience what might be called weak anti-localization instead, thereby increasing the probability of not being scattered at all, and therefore the conductivity of the system. It appears to be more conducting than the classical system without this interference taken into account. And for sure, more conducting than an ordinary semiconductor with the backscattering enhanced. However, that was theory, whereas in experiment, they didn't seem to observe either, nor weak localization, no weak anti-localization related behavior. At that time, it had been known already what to look for because of the previous studies carried out in gallium arsenide. People would know how to identify the features indicative of weak localization or the lack thereof. Okay? But it looked kind of neither. And so it took some time to develop a scenario where we would indeed predict some weak anti-localization, which would then have to cross over to the conventional localization type of behavior. And that's because the former would be there as long as one can limit the analysis to a single Dirac point. That when all the momentum, scattering momentum space occurs with small momentum deviations from a single Dirac point. As temperature or magnetic field decreases, the scattering between the two Dirac points becomes important. And that's the one which reverts this behavior back to being weakly localizing. Okay, so one can only find some features exhibiting anti-localization at sufficiently large fields, but not in the immediate vicinity. Furthermore, one could, come up with certain models of disorder which result in, accidental or not, cancellation between the two, and so the plots would look more like these, rough lines as opposed to what one would expect on the basis of the weak localization versus anti-localization theory. Okay. So that was interesting, also because it sort of stimulated a further study into the properties of disorder scattering through transport and other means. And what the community came up with was this notion that, well, perhaps out of the different types of disorder, the most relevant one was the so-called ripples. Okay, and ripples are literally the folds and the frozen phonon modes, essentially, of the graphene sheet, which, mathematically speaking, would represent the fluctuations not of the potential nature, like the static electrostatic potential, but as if it were a random magnetic field of a kind. And mathematically, it was a sort of challenge to properly treat this kind of disorder, where the random variable would be the vector potential as opposed to the scalar one. But it was done and resulted in some predictions. In particular, it was interesting to see how those two different mechanisms would be possible to distinguish based on the typical transport measurements. Turned out that the transport times, for one, would not discriminate between the two, but say the cyclotron times, which would again require an application of now weak magnetic field, would be the means of deciding as to which mechanism dominates. Okay, so there were some predictions made to that effect. And finally, I'll just scroll through the topic which I advertised before, that is how to mimic holography in graphene. That part of the story starts with some analysis of the interaction with the phonons, the elastic modes of the graphene sheet, of which there are two kinds, in plane and out of plane, or flexor, so-called modes, and it's the latter which turn out to have greater effect on everything. Apart from the other details, what's interesting is that if one uses some kind of suggestive, gravity-like notations, it's possible to represent this interaction very much like the one in some theory where there is a non-trivial metric, and Dirac fermions propagate in that static but non-flat metric and interact with the corresponding metric tensor. And then one can suggest a sort of a demonstration for how something similar to a much expected holographic behavior works. Well, imagine having this graphene flake as a perfect circle where we can pinch the point in the middle and pull on it, thereby turning it into this kind of a trumpet thing. And of course, that changes the geometry from flat to that of the surface of rotation. All right. Now one can ask the question, well, if there is a fermionic mode living on the boundary, and usually because of the so-called edge reconstruction, there would be an edge mode, or not chiral, it's not quantum Hall effect, propagates both ways, but it's confined to the edge. And one can wonder, how does the spectrum of that and the behavior in general of that edge mode depends on the geometry which was artificially created in the bulk by pulling on that central point, by changing the geometry? The answer can be obtained as follows. On the one hand, one can use this, which I'm not going to discuss, but we'll be happy to do privately. One can use the holographic prescription for computing the corresponding propagator, which is solely dependent by the metric and the bulk. On the other hand, one can try to reproduce the same behavior based on a certain phantom, like non-existent phantom interaction between the electrons living on the edge. Okay, specifically in the following terms: if we create a certain profile, and for simplicity, that profile in the middle can be chosen as a power law, which simplifies calculations a lot. And we can think of some hypothetical interaction on the boundary, which is a power law too. The question is how to relate these exponents in order to see the manifestation of that geometry in the bulk that would result in the same behavior of, say, the single particle propagator, or something more physical that can be directly measured. We call it time of flight experiment, tunneling, power, the noise power spectrum. All these are established experimental probes. So in order to compare the two, again, one can choose that profiling function at will, so eta would be chosen, and then it will turn out that the electrons at the edge behave as though there was a certain interaction between them, which is not there. Okay. What they feel is the geometry of the bulk. And in a sense, and one can mimic a number of interactions, not only the so-called Latinger type of behavior, but for example, the rather peculiar behavior associated with the Coulomb interaction in 1D. It's a sliding density wave, so-called. And even more exotic ones. So what this all looks like is essentially as if the equivalence, Einstein's equivalence principle, were turned 90 degrees. Right? The interactions between the particles propagating along the edge are sensitive to the geometry, which is the bulk geometry, sort of at 90 degrees with respect to the direction of their propagation. Hey. What happens? Froze. Come on. Yes. Yeah, there is still something. And so, after basically having advertised this, without going into the details, let me summarize by saying that, yes, the Dirac fermions in graphene provide this kind of desktop environment for, if not studying seriously, but at least demonstrating some of the peculiar phenomena which would have relativistic nature and which might be difficult or even impossible, most likely impossible to observe in our real universe. So there is this propensity in graphene towards exitonic pairing, but whether or not it actually gets materialized depends on the actual strength of that interaction with all the other factors included, which obviously the early studies did not. Magnetic field could be a factor supporting this mechanism and making it happen, even for relatively weak interactions. And then there's a number of experimental probes that would reveal the presence of such gap. And again, as I said, some of them were quick to report it, but the later ones did not. So we don't know. And it's somehow nice that almost 25 years after the early work, the community seems to be returning to the same topics, now at the new level, albeit without much reference to that naive early attempt. So perhaps we'll soon learn more and better. Thank you.
All right, thank you, Dmitri, for this nice review of Dirac physics. Any questions?
Well, you just said it, review of Dirac's physics. So I suggest you write a review paper about this along the lines of your talk, which was extremely instructive. I learned a lot from it. And writing a review paper would force people to take note of your earlier work.
I think it's too late, frankly. I could have done it at the time, but it was sort of premature, I guess. Before the field picked up the momentum, I already switched to other things. And for the past 10 years, my only obsession was with the condensed matter-related holography, which I, on the one hand, like very much as a general idea, but absolutely disagree with the way some people practice the topic.
Well, still, very interesting subject.
Once I retire.
But talking about too late, actually, many years ago, I wrote a few papers on superconductivity of Dirac fermions. Mm-hmm. That was before graphene. So we were interested in actual Dirac fermions, real relativity.
Yeah, 3+1.
Yeah. Exactly. And it turns out that the basic idea was to look at how would BCS theory or Bogoliubov-de Gennes theory look if the basic equation we start from is Dirac's equation and not Schrödinger's equation. Mm-hmm. And then as Dirac fermions are described by 4 component spinors and not 2, just as you also pointed out, it turns out that there are more different type of pairing states. and so more different types of superconductivities in the plural. Where in non-relativistic superconductivity, there's only singlet and triplet superconductivity. There are three components to it. In relativity, there are a total of 16 different components, which can be classified in 5 different covariant objects. So that is some full-scale, real relativistic Dirac superconductivity. And as I was listening to your talk, I was wondering how much of those additional states could probably be found in your calculations and in graphene.
Absolutely. Thank you for bringing up this point. This is a PDF file, so I cannot unhide the one in the PowerPoint, which was exactly about the different masses, which I thought would take the discussion farther away. Even in 2+1, which is the environment here, one can contemplate the idea of different masses, which are not all singlets for all 4. The largest symmetry group. I don't remember the exact number, but one can make quite a number of those by particle two fermion order parameters, some of which can be identified as different types of charge order, some as spin order, and yet others as combined spin/charge. My understanding is that people have actually discussed a number of those in the context of the sort of theoretical graphene with the short-range interactions, where everything is sensitive to the exact terms that one puts into that interaction, part of the Hamiltonian. If I remember correctly, the on-site interactions tend to favor the charge, whereas the inter-site spin density wave, if they're comparable, that may result in a mixed order. And this is zoo of the different phases has indeed been explored. Igor Herbut would be one name that comes to mind who did that also in the late 2000 or so. Since then, I haven't seen much of the following discussion on the topic. People seem to be comfortable with the notion that they don't observe any gap at all. And indeed, yeah, one could try to carry out a more detailed analysis energy-wise, because what actually determines the stability of those types of order is relative energies. In the RPA approximation, they probably have all same energy, so one would have to go further to find the means to discriminate between them. Nice project for a student, it could be, I suppose. Yeah. Right, thank you.
Any questions? I didn't understand the status of the gap now. I mean, this last paper, that very recent one that you mentioned. So what exactly do they report?
Yeah, I showed those data on RPS, tunneling, and transport.
But they were early experiments.
Earlier, yeah.
But there was, I think in the end you mentioned, after you talked about magnetic field, you mentioned
anywhere from 10 to 100 Kelvin. Remember, 1 electron volt is 10,000 Kelvin. So that's how big or small. It's actually quite sizable compared to the temperatures at which these experiments would typically be carried out.
But this paper with Game, I think, and Novoselov, that I think was out this month or like last month. What was the statement of that one?
I don't remember.
It was.
I thought it was.
I think it was about magnetic field and.
Yeah, I thought it was in the 10th digits, but we can look it up to see what they actually. Well, it's field dependent, of course. So yeah, but within a typical range.
Okay. And about this holographic application that you kind of flashed, but so you're thinking of how holography would kind of alternatively describe the system, but what is the real life?
I would call it holography light.
What about this situation of curved sheet of graphene for like in real life? How would you model these effects? And is there like any?
Yeah, well, hypothetically, one could make an exhibit in the Science and Technology Museum for the kids to come and turn the knob. By doing so, they changed the geometry of that trumpet, right? And then measuring the tunneling exponents, say, to the edge and from the edge, one could see the effective interaction between those electrons changing as the curvature increases or decreases.
Computable? I mean,
Yeah.
So
Nobody
what
attempted this,
changes in
obviously.
theoretical computation?
Theoretical.
Yeah. So what changes in this case?
Well,
If you do, I mean, not holography, but if you do real condensed matter.
Well, it looks like, I would say, if one were to find an argument in favor of holography, they would probably refer to something like this, but doesn't require any physical new principles. It's just the way it is. So the point is that, again, the changing bulk geometry affects, well, literally the, if you like, action computed along the geodesic, right? This is an action of what?
I mean, condensed matter calculation. So you have a
Condensed
lattice.
matter calculation is what I call 1D Bosonization, but it's not a standard one. Standard Bosonization only works if the interaction is point-like, contact interaction. In order to handle longer ranged, let alone power law interactions by bosonization, one has to, well, use a certain extension which, strictly speaking, is not well justified. But everybody does it, after those who are in business. Right. And that's how you can compute independently that green function and try to match it to the holographic prescription. Basically, it says compute the action in the bulk between the points on the boundary for a given geometry. So you have to use the geodesic, right? And then the propagator, the holographic propagator, will be governed by the dependence of that action. Right? And then you can compare this predicted behavior to what the pseudo-bosonization approach yields. And that's how the matching can be done.
Okay. Yeah, I'm not sure there are any results of this matching, but so far. Okay, any other questions? If not, let's thank Dmitri again.
Thank you.